All right, good morning, everyone. So we were talking about, at the end of yesterday, mechanisms for energy transfer. So how energy actually transfers from one system to another via heat. Right? So yesterday we were talking about conduction. Today, the next one we're going to talk about to start off with is what's known as conduction. So conduction is the flow of energy via direct contact. What's called conduction. So for example, if I took my frying pan and I put it on my stove, so let's say this is my frying pan and I put it on the burner, what happens in that case is the burner's at one temperature, frying pan's at another temperature, but we notice that the burner would be at a higher temperature, which means that the atoms inside of the lattice would be oscillating much faster than what they are inside of the frying pan. So what happens in that case then is that the oscillation, the amplitude is bigger, the frequency at which they're oscillating is bigger, so they start making collisions, conservation of momentum, with then the particles which are inside of the frying pan, which causes them to then pick up energy via conservation of energy momentum. So they start oscillating faster, and then in that case, they kick the next ones next to them, which kicks the next ones next to them, which then eventually causes it to slowly propagate through until eventually the frying pan will be at exactly the same temperature as the burner. But it starts off in a small locally area on the bottom of it, and then again starts to kind of dissipate all the way through due to the collisions that the atoms are making inside of the actual object itself. So this is what we call conduction. So conduction is the flow of energy from one object to another object via direct contact. So this one we can actually quantify. So let's say we have two different objects here. So let's say this one over here is my hot source. So I have T hot here. And then over here I have T cold. And then I'm going to connect these two sources together by some object. Let's say my object in this case is like a rod. So here's my rod. So my rod in this case has a length of L, has a cross-sectional area down here, A. And then we're going to have a temperature gradient between the two. So what I want to know then is, what is the power? So remember, power in this case is the rate of change of energy, which in this case, the energy is going to be the heat divided by the change in time. So we want to know, what is the rate at which energy is transferred from the hot source to the cold source? Because in this case, we have heat flowing in this direction. We want to know the rate at which this is going to happen. So let's think about each one of these quantities. What do you think would happen to the rates if I make my rod here long? So let's say these guys are really far separated away from each other, so I make it much longer rod. Would that increase the rate or decrease the rate? So would it take more time for the energy to transfer from one side to the other side, or less time if I made the rod really long? More time, right? So that means that what? This thing then has to be inversely proportional to the length, right? So the rate is going to decrease as I make the rod much, much longer. So what I know is that this thing has to then be inversely proportional to the length. Cool. That's our first observation. What's our second observation? What about the cross-sectional area? So what would happen to the rate at which energy would transfer from one side to the other, or how long would it take for the energy to transfer from one side to the other if I made my cross-sectional area bigger? So for example, if my rod only had a cross-sectional area like this versus this, which one would allow more energy to flow more quickly? Good, the bigger one, right? So that means that the rate then should be directly proportional to the area. So the bigger I make that cross-sectional area, the faster it's going to transfer from one side to the other, but the longer I make it, the slower it's going to transfer. And the last thing we can look at is, what about the change in temperature? So this temperature gradient. Would it go faster if I had a bigger change of temperature between these two sides? So for example, this was at 100 Celsius, or this was at 0 Celsius, or would it go faster if I had a smaller temperature difference between the two? So if this was only, say, 100 and this was 99. So which one make it go faster? Would it, being a large temperature gradient, cause it to go faster, or a small temperature gradient? What do you think? So which one would want to transfer energy more? Large temperature gradients or small temperature gradients? A large temperature gradient, right? Because if I had a large temperature gradient between two things, energy wants to flow more rapidly from the high temperature to the cold temperature to equalize the system as fast as possible. But they're only separated by like 1 degree. It's not a big deal, so it's going to take more time for that to happen because it's only going to be a little bit, I only need to increase it a little bit, so it doesn't really want to do it. The bigger the temperature gradient is, then the faster that this process is going to happen. So if I put all these things together, what this tells me then is that the power, or the rate at which energy is transferred, is then going to be equal to what? The area divided by the length, all times the change in temperature. So it's proportional to this guy. Now, to make the two sides equal to each other, we have to put in a fudge factor, a constant. That constant says that the to the, again, heat divided by the change of time is equal to K times the area divided by the length, all times the change in temperature. K here, make sure I get my right terminology here, is what's known as the thermal conductivity. K equal to the thermal conductivity. So based off of this, this thing has units of what? Meters. So area divided by length is the same thing as meter. This thing has units of temperature. So this thing has to have units of per meter temperature. And then on this side, I have to have watts. So this thing has to have units of watts per length per temperature. So this thing has units of a watt per meter per Kelvin or degrees Celsius. Either one of these is sufficient. Either one is sufficient. So what is thermal conductivity? So thermal conductivity basically only depends on the type of material. So this thing depends on the material. So any different material has its own different thermal conductivity. So depending on the situation, I either want to use a large thermal conductivity or a small thermal conductivity. So for example, if K is large, what that does is it massively increases the rate at which the energy is transferred, which means if I really want to transfer energy from one system to another system, I want to use something which has a large K value. For example, my frying pan. If I want to eat sometime today, I want to have a K value that's very large, right? Because I want the rate to be very quick, which means I want the energy to transfer from the burner to the frying pan, so that way I can actually eat sometime today instead of waiting until next week to actually be able to cook my food. Okay? So in that case, I want to have a large K value. So if I want to transfer energy very rapidly, I want to have a large K value. So most metals, for example, are thermal conductors, which means that they have a very large K value. So large K is large, it's a thermal conductor. Which means that it transfers energy, or at least thermal energy, very rapidly. So this is going to be something like a metal. If I don't want energy to transfer from one system to another system very rapidly, I want to use something which has a very small K value. For example, you go out in the wintertime. What do you wear in the wintertime? Clothes, right? A coat. For example, if you're from where I'm from, which is much further north, upstate New York, most people wear down jackets. Right? Why do you wear that? Down jackets have feathers on the inside. What the feather does is it puts an insulation between the two, but more appropriately, what it actually does is it reduces the rate at which energy is transferred from the one system to the other system. In this case, the one system is you, the other system is outside. So when you come outside and your temperature is at, what, 98 degrees, outside can get down to minus 41 degrees Fahrenheit. You want to stay as warm as possible, so in that case, you have to wear something like a down jacket, which has a very small K value, so in that case, the rate at which energy is transferred is very small, so it takes a long duration of time for you to lose all of your heat to the outside. So something which is a small K value is then a thermal resistor. doesn't allow energy to flow from one system to another system. So this is going to be something like, again, down. It's going to be something like you put in your house, right, in between your wall and the exterior wall, you have insulation, etc. All of these things are thermal resistors. They don't allow for a huge amount of energy to transfer from one system to another system. At least it takes a long time for the energy to transfer through. So this is what we call conduction. So conduction, again, is the transfer of energy from one system to another system via direct contact. And the way that this happens is that the rate at which it transfers is, again, K, which is this thermal conductivity, times the area divided by the length, times the temperature gradient between these two. Where am I erasing? There, right in front of my face. Okay. So let's use this and let's do an example. The example says that we have a concrete wall. So here's our concrete wall. So this concrete wall is 2 meters high. So in this direction, it is height of 2 meters. Let's call that H. It is also 0.2 meters thick. So in this direction, this is our thickness T, which is equal to 0.2 meters. And what else is it? It is 3.65 meters long. So in this case, let's call this the length. So this is 3.65 meters. So in this case, we want to find the energy which is transferred in the amount of time, delta T, which is equal to 1 hour, which is 3,600 seconds. If there's a temperature gradient between the inside and outside. So let's say this is my inside temperature. So it's my hot temperature, which is at 20 degrees Celsius. And on the outside, I have my T cold, which is equal to 5 degrees Celsius. So we want to know how much energy is transferred from the inside to the outside in amount of time of 1 hour if the thermal conductivity of the concrete is equal to 1.7 watts per meter per Kelvin. We want to know what is the energy or the heat which is transferred. We want to know the total amount of energy. So basically starting off with power, we know that the power, again, is equal to our K times the area divided by the length, all times the change in temperature. Well, we also know P, which is the power, which is the heat divided by the change in time. So all this says then is if I want to know the total amount of energy or the total amount of heat which is transferred, all I have to do then is multiply both sides by delta T. So from here, this simply says that my heat then is going to be equal to the thermal conductivity times the area divided by the length, all times the change in temperature times my change in time. So in this case, we have to determine, actually, let me call this little l so we don't get confused, which L we're actually talking about. So in this case, we have to determine what is the area and what is the L in this case. So think about what each one of these is. So again, A, in this case, is the cross-sectional area. L is the length between the two sources. So we need to know which one is which in this case. So what's going to be the cross-sectional area and what's going to be the length? What's my area? First and take shot. What's my area?
Is it 2 meters times 3.6?
That's right. So in this case, the area is simply this cross-sectional area, the area of the face, which, as Brisson just said, area then in this case is equal to H times L. So in this case, that's the 2 meters times the 3.65. And what's the length then? The other one, the thickness, right? So good. So let's put all those things in. So this is then going to be equal to thermal conductivity times the height times the length divided by the thickness, all times then the change in temperature times then the change in time. So let's plug everything. So this is 1.7 times 2 times 3.65 divided by 0.2 times my change in temperature, which in this case is what, 15 degrees. All times my change in time, which is 3,600 seconds. So the look at numbers we find in this case then is it turns out to be 3.35 times 10 to the 6th joules. That's actually a huge amount of energy, which you have now just lost because of thermal conduction. Okay? So look, so this is a conduction. So the last thing we'll talk about for energy transfer is radiation. We'll talk about radiation. So radiation is the transfer of energy via light. So this is radiation. Now, one thing to note, and we'll talk about this actually more next semester, but it turns out light doesn't need a medium to actually propagate. So what that means is unlike convection and unlike conduction, both of those two need a medium for the heat to travel through. So if it's convection, it needs the exterior air, for example. If it's conduction, it needs whatever the material is that connects the two, which could be a metal, could be a wood, could be insulation, whatever. But light travels in space, where in space there is no medium, which means it actually doesn't need a medium. So radiation can travel anywhere. It doesn't actually need some sort of medium to actually propagate it. So this one is independent. So how does this one work? Well, we already talked about when we talked about making thermometers that anything which has a temperature gives off light, which basically means that all of you, as you're sitting in your seats or as you're standing there, what you're actually doing is you're emitting light, you're emitting radiation off in every particular direction. So you are constantly giving off energy due to the fact that you glow. Not in a spiritual sense where you glow. Or a woman that's pregnant, she's glowing, right? Things like that. What I mean is you have a temperature, therefore you give off light. You glow. So it turns out that all objects which glow at a particular rate, which means that the energy which is given off at a particular rate. So let's first talk about black bodies. Or perfect absorbers as well. So what's a black body? A black body is an object which fully absorbs radiation. There's also what's known as a perfect emitter, and this works out exactly the same way for a perfect emitter. So a black body is an object which completely absorbs, doesn't give off any light. It absorbs light. Or a perfect emitter here is something which only gives off light. Doesn't absorb any light. So a good example of a black body, at least in theory, is a black hole, for example. Completely absorbs all the light, doesn't actually give off any light at all. So it turns out that for either a black body or for a perfect emitter, the rate at which the energy is given off, so the power, which again is the heat divided by the change of time, is equal to sigma times the cross-sectional area times temperature to the 4th. Where sigma is what's known as Stephan's constant. is equal to 5.67 times 10 to the minus 8 watts per meter squared per Kelvin to the fourth. I'm sorry? Either one. Either one. Yeah, so the difference is for the black body, this is the rate at which the energy is being absorbed. And for the perfect emitter, this is the rate at which the energy is being emitted. So it actually works for both ones. So good question. So yeah, so for this guy, this is the rate at which it is being absorbed. I know how to spell. Great. And then for this one, this is the rate at which it's being emitted. Now, let's use that and bring that back to us. We as people and most basic objects are not either perfect absorbers and are not perfect emitters. They're somewhere in between. So us as humans, we do both. We radiate and we absorb simultaneously. So I absorb coal's radiation, but I also emit radiation onto coal from me, so the two of us are actually constantly exchanging radiation, and I also exchange radiation within my environment as well. So the sun, table, anything else, the lights, all these things are actually giving off and absorbing energy at all times. So for us as humans, since we're neither a perfect absorber or we're a perfect emitter, we're somewhere in between, which means we can use this as our base reference and put an extra fudge factor in there that basically says that we are not perfect, but we're somewhere kind of in between. That fudge factor we're going to put in is what's known as the emissivity. Let's write that down. So for us, turns out that our power at which we give off and absorb is equal to the energy per unit time is equal to epsilon, where epsilon is what's known as the emissivity, times then the Stephan's constant times the cross-sectional area, times then temperature to the fourth. So this guy is the emissivity. Emissivity has no units to it, so this is a dimensionless quantity. So basically, the emissivity is going to be somewhere between 0 and 1. So in this case, let's say this is the amount of power that I radiate. So this is the amount of power which I'm radiating. If it was 0, in that case, I would be a perfect absorber, which means that I would be a black body. If it's 1, then I'd be a perfect emitter. So in this case, this would be then our black body. This guy would be our emitter. So again, a person, a table, your desk, outside, anything is going to be somewhere in between these two things. So I would have to know exactly what that number is for a different object. So typically you would have to be told exactly what the emissivity is of the objects so you can actually proceed through the problem. So for a typical person, again, what's happening is they're giving off light, but simultaneously they're also giving off light, or sorry, absorbing light, which means that they're in kind of a delicate balance of how much it is that they absorb versus how much it is that they radiate. So if I wanted to know me as a person standing up here, constantly giving off radiation and then constantly absorbing radiation, if I wanted to know if that radiation would heat me up or cool me down, I can then look at the total power. So in this case, my total power then would be equal to the power which I radiate minus then the power which it is I absorb. So in this case, what's going to be the same is I'm still talking about me, so this is going to be my emissivity times my cross-sectional area, but in this case, this is going to be my radiated temperature, so the temperature which it is I'm at, minus then the temperature of the environment. Because in this case, what I'm doing is I'm absorbing this energy from the environment. Now that environment includes you, includes the table, includes the UV lights here, all of these different things. So basically what this says then is that my total power radiated is going to be positive if my temperature is greater than the environmental temperature. So this is what happens in the wintertime. I go out in wintertime, it's colder outside than it is for me, so I give off light, which then causes my body to emit more light, or not emit more light, but emits more energy than what it is I'm absorbing, which means eventually I'm going to get cold. Summertime, the opposite is true. In that case, I have my temperature, the environmental temperature is higher than what I am, which means I'm going to absorb more energy, which means eventually I'm going to increase my temperature, and I'm going to get hot, not happy, and probably grumpy. I don't like being hot. Anything you get out of this class? No, I don't like being hot. Great. So, in this case, again, everything is giving off light, everything is emitting light, so you're simultaneously radiating and absorbing, and the rate at which it is that you are, in this case, radiating is just the difference between what it is that you're radiating minus what it is that you're actually absorbing. So this is radiation. So all things which have a temperature give off light. The rate at which the energy is lost due to that light is given by this. Right? I'm sorry? Yes. Thank you. Thank you, Edith. So these are mechanisms of energy transfer. So these are the three ways that in general we can then transfer energy. So what's a good example of all of this stuff? The best example of all of this is what's known as a Neuroflask. So let's talk about a Neuroflask real quick. Neuroflask. So what's a Neuroflask? Well, a Neuroflask is basically a thermos. So what does a Neuroflask look like? So typically it has a small cross-sectional area in the top, which goes down and then tapers off typically to something much larger. But on the inside of this thing, usually what happens then is this is actually created from a hollow inside portion. So this is my hollow inside where the air is actually usually being evacuated outside. And not only is the air evacuated on the outside, it's silver lined on the inside of this, or basically mirrored. So typically what happens here is you have a small cross-sectional area. Inside of here is hollow and vacuumed out. And there's a silver line on the inside. This portion here has a silver lining, or at least mirrored on the inside. Mirrored. So if any of you have ever worked in catering before, you know, you have those big old coffee thermoses that you fill those up with. Those actually have mirrors on the inside, and you know that because if you hit one against something, the mirror on the inside breaks, which is fantastic, and then you can shake it around and hear the mirror. It's simultaneously cool and you get in trouble. So I did that too many times. So the question is, why, going through this Neuroflask, why did somebody bother to make this thing? Right? So let's think about what you're going to use your Neuroflask for. So you're going to put your hot coffee in there. You're going to make your mama's soup, put that in there, right? Especially if you have a sickness, you have a cold, something like that. So why would somebody go through the trouble to make all of this stuff? Why is it that we have a small cross-sectional area on the top, that we've actually put a hollow chamber on the inside that is vacuumed out, and why do we silver the inside? So why would we go through all this trouble to actually make something to ensure that we actually have hot soup later today or hot coffee later today? Or cold soup. Keep things cold too. Or cold coffee if you like iced coffee. So why would you go through all of these things? So what are you trying to minimize? What is each part of these trying to minimize? The heat loss, right? So what I'm trying to do is decrease the overall rate at which the energy is being lost. I want to decrease the amount of power, right? So what are each one of these individual sections doing? So why would I have a small cross-sectional area on top? What am I trying to minimize in that case? So which type of mechanism am I trying to minimize? Convection, right? So in this case, the part of the small cross-sectional area here is trying to minimize convection. Because what's going to happen is anytime I open my thermos, air is going to leak out, which means it's going to carry energy away via the flow of the air on the way on the outside, which means that it's actually carrying via the direct flow of medium in this case. So the smaller I make the cross-sectional area, the less ability the air has to come out, which means I'm minimizing the convection. Why would I hollow out the inside? Conduction, exactly. So in this case, when I'm trying to hollow out or minimize conduction, right? Why is that? Well, it turns out that vacuum has a K value, a thermal conductivity, which is very, very close to 0. Which means that if I evacuate the air on the inside, then I have no medium directly contacting from the outside source and the inside source, which means I have no ability to flow the energy via conduction. So the point of evacuating this is to limit conduction. Why would I mirror the insides? What's the last one? Radiation, right? So in this case, what I'm trying to minimize then is radiation. So why is that? Well, on the inside, this thing is hot, which means it's giving off light, but the light which would then travel through the walls would then hit the mirror, bounce back, hit this mirror, bounce back, which means that the light would be stuck on the inside, basically bouncing back and forth between the two walls, which means I would also minimize the amount of energy which is being lost due to radiation. Now, of course, we would still lose a little bit via radiation because no mirror is 100% reflective. So in that case, we still leak out a little bit. This is what creates a laser. Okay? We can vacuum it, but we can't vacuum it down to a perfect vacuum, so we're still going to have some small non-zero K, so we are going to have some conduction loss. And again, whenever time we open it up, we lose energy due to convection, but this is about the best we can actually do. So this is what a Neuroflask is. So Neuroflask takes all of these different things into account and tries to make something which is going to make sure that your coffee or your soup or whatever stays either hot or cold for the entire day. Okay, so these are our mechanisms. So the last topic we'll talk about in this class is what are known as entropy. This is our last topic for this class. So what is entropy? So entropy has to do with things which are known as reversible or irreversible processes. So reversible versus irreversible. So what's a reversible process versus an irreversible process? So the easiest thing to talk about first is what's an irreversible process. So in this case, if I have this spray bottle sitting on this table and I do that, and it falls to the floor, this is what's called an irreversible process. Why is it an irreversible process? Because the bottle doesn't spontaneously jump back onto the table. If I break an egg, will the egg automatically mend itself? No, that's an irreversible process. If I make a pizza, will the pizza spontaneously unbake itself? No. So irreversible processes are processes which occur in one direction. So this is a process which naturally occurs in one direction. A reversible process, then, is a process which goes in multiple different ways. It goes both directions. So this is the process which proceeds in both directions. So if we can have a pizza make itself and then unmake itself, that would be a reversible process. So it actually proceeds in both directions. Now, the question is, in nature, how do we distinguish the difference between an irreversible process versus a reversible process? Well, it turns out that if we talk about conservation of energy, the energy would be conserved if this thing jumped back up onto the table. So I would have exactly the same amount of energy if I did that versus this thing jumping back onto the table and getting back to the same exact location. So it can't be conservation of energy which distinguishes the two, because there's no difference in conservation of energy whether that thing fell off the table or jumped back onto the table. So it can't be conservation of energy. What actually distinguishes these two is what we call entropy. So the distinguishing factor is called entropy. So what is entropy then? So basically, we're going to be spending the rest of the semester kind of describing entropy in different situations. So for us right now, we're going to look at the viewpoint that entropy is a measure of disorder within a system. So what does that mean? So that means that I, this later, have a system which is fully organized. Okay? This is something which has entropy. This would have what's known as a low entropy. So in this case, anytime I have something which is fully organized, this then has a low amount of entropy. If I do that, this is the system of high entropy. In this case, I have a very disordered system, which means my system has gone from a low entropy in here to a system of high entropy, which is now scattered throughout the entire place, which unfortunately I have to clean up. So this is entropy. So what entropy does is it measures the disorder of the system. The more ordered the system is, the smaller amount of entropy that it has. And it turns out that in nature, almost everything seeks the ability to go from a low entropy system to a high entropy system. Ask my children. They will tell you that. Actually, they won't tell you that. They will show you that. Okay. So all systems, well, not all systems, but it turns out that if I was dealing with an irreversible system, all irreversible systems have to have an entropy which increases over time. If I was dealing with a reversible system, it turns out that the change in entropy remains constant. So the distinguishing factor between the two is that the change in entropy must be greater than or equal to 0. Where this thing is greater than 0 for an irreversible process, and it must be equal to 0 for a reversible process. This statement is basically what's known as the second law of thermodynamics. So what the second law of thermodynamics says in terms of disorder is that all systems have to have a change in entropy which is greater than or equal to 0. Now, two things to note here. Note number one is the actual value of the entropy, just like the actual value of potential energy, doesn't matter. We don't care about the actual number at which the entropy is. What we care about is how does the entropy change over time. So that's the first thing we want to note here. So note number one is the value of entropy doesn't matter. Only its change. The second thing to note is that we can actually violate, and we do violate, this law all the time. And what do I mean by that? And this is going to be a distinguishing point of this guy. So it turns out that you can have a system which actually has a negative change in entropy. A good example of that is you. you start off as what? An egg, which means that you start off in a particular entropy state, which is very disorganized. Then as you get born, right, as you become an embryo and et cetera, now you have portions of that cell, of that egg, which now become specialized to something, right? Whether it be skin or bone or organs or et cetera, which means that you've actually decreased your entropy because you went from a highly disordered system, which is just one egg which had a disorder to it, to now a fully organized system. So you've actually decreased your entropy. A tree, things like that, all of these things will all have the same thing. They all actually will decrease the amount of entropy. Now, if I consider only myself can have actually a decrease in entropy because I would be considered a subsystem of the entire system. So if I was talking about a single object, that single object actually can violate this law because it can actually have a negative change in entropy. It can actually go from a disordered system to an ordered system. For example, I don't want to do this, but when I pick up all of the chalk and I put it back in here, I've actually decreased the amount of entropy. Now, what does this thing say then? What this thing says then is the change in entropy for the entire system must always be positive or equal to 0. However, the change in entropy of a subsystem within inside of that system, that then can be negative. That can decrease. So here we have to be a little bit careful when we're thinking about our thermodynamic systems. So we have basically the entire system. Inside of here, we have basically subsystems. So each one of these is a subsystem. Now, again, it is entirely possible that the subsystems here can have a change in entropy which is less than 0. This is allowed. But this might be a reversible process, so this change in entropy might be equal to 0. This one might be positive, et cetera, et cetera. Well, what has to be true is that for the entire system, the change in entropy must be equal to 0 or positive. Right? So here, when we talk about the second law of thermodynamics, what we really mean is that the change in entropy for the entire system, this has to be growing or equal to 0. But a particular subsystem within inside of the system can have a negative change in entropy. This is absolutely positive. This is possible. Okay with this? So this is the second end. So subsystems can have a change in entropy which is less than 0, but the entire system this can't be changed. It can either be 0 or positive. So typically, we have to be careful in how we define our systems to actually incorporate the second law. So the next question is, well then how do we actually calculate entropy? So how do we actually calculate entropy? Well, the way we calculate entropy is going to depend. So how do we calculate? So let's start off with a basic idea. So let's say we have a process which goes from state A to state B along an isothermal process. So remember, what does isothermal mean? What's constant? Temperature, right? So in this case, if I have an isothermal process, then my change in temperature is 0 because I have a constant temperature. So in this case, we then say that the change in entropy for the system then is going to be equal to the heat flowing into the system divided by the constant temperature. So this is entropy. So here, this is the heat flowing into the system divided by our constant temperature. But if I have a system going from A to B, along a non-isotherm. How do we calculate it in that case? Well, in this case, since the temperature is not constant, in general, then the heat will be a function of the temperature, which means in this case, our change in entropy must then be equal to the integral from state A to state B of the heat flowing into the system divided by the temperature. So this is then entropy. Okay? Now here, if the temperature is constant, in that case, if this would come out, I'd have the integral of dq, which would then just be q in this case. So yeah. So here, and it's a non-isotherm in general, dq is a function of T. So I'd have to know exactly the thermodynamic process to know exactly how it is a function of T. Once I know that, then I can actually perform this integral. So in this case, I would have to know the exact process to find dq as a function of T. Okay. So I have an example to do for you, but it's going to take me more time than we got, so we'll just call it a day, and then we'll do that example first tomorrow. Those are the entropy. We'll talk more about that later. All right, so have a good day, everyone. I will see you tomorrow after I spend half my day trying to clean up the mess I made. So.